All right, welcome everybody to my talk, and special thanks to the organizing committee for this wonderful conference and for inviting me to speak. It has been really interesting so far. I've really enjoyed many of the presentations. So I'm going to talk about aspects that arise when you teach signal processing to people who major in music or humanities instead of engineering. Oops. So first, some background and motivation for my research project. That's me. The picture is obviously from the time before I started working with compilers. I look a lot younger and healthier, right? So my current post is a lecturer of signal processing and recording arts at the University of Arts, Helsinki. I graduated from music technology and performance from the same university. Currently, my PhD thesis is in pre-examination, so it's pretty far along. I hope to defend in January. And I've done research and development in musical signal processing and programming since the early 2000s. And I've also been teaching C++ and signal processing since then. So my research background is from PWGL. Maybe some of you have heard about that environment. It's a LISP-based composition programming environment that you can use for algorithmic music, music analysis, integrating notation and algorithms, stuff like that. I designed and implemented the PWGL synth module, which is the real-time software synthesizer you can utilize within PWGL. And this is a small example of what it looks like. So it's a patching interface, and we designed it primarily to work for oralization of scores by physics-based models. For example, you could load in a musical notation score of a piece for guitar and then play that piece back on a virtual guitar model. So with that in mind, we designed PWGL synth with a couple of features. It was pretty simple, so it's just an interpreter for unit generator graphs, but it can do sample granularity and unit delay feedback. So that's a requirement if you want to do physical modeling. You need to be able to connect signals back and forth with minimum latency. So from those features also arose a couple of problems that we have to face. One of them is that, obviously, as Jan said before, an interpreter is never as efficient as compiled code, and especially so if you enforce this constraint of working with one sample granularity. So computers were fast enough that it could do pretty extensive signal processing routines in real time, but of course the performance would be far below the theoretical machine limits, so to speak. Most of the time the processor was actually looking for the code it wanted to execute rather than computing. And that's not something we want if we desire high performance computing and signal processing. Also because it was written in C and it's a simple interpreter, it differs syntactically from the rest of PWGL, which is Lisp based. So you have this boundary of different ways of thinking in the algorithmic composition part of your patch and the synthesis part of your patch. And maybe that's something that cannot be avoided, as the domains are very different and have different performance requirements, but still it creates some schism in the environment because you kind of have to program in two distinct languages to accomplish your goals. Okay, I set out to solve some of the problems we had with PWGL synth, and this project eventually morphed into what's nowadays called Kronos, which is my PhD project. And the very first step I did was that I wrote a simple machine code translator for PWGL synth. So instead of the interpreter loop, I would generate a blob of native code that would just call directly the boxes in the patch. Then I started replacing some of the simple boxes like adds and subtracts with native instructions. So it became more and more like a compiler. But at some stage, I realized that there's only a limited amount of things I can accomplish in this way, because still the syntax and the design are governed by the limits of the interpreter that we designed against. So eventually I figured out that I need to do a fresh start, design a language entirely for signal processing, and to avoid all these constraints in the first place. And initially my conception was that of a visual modular synthesizer, but as I wanted to incorporate more and more capabilities and get rid of more and more things that frustrate me in graphical programming languages, it became more and more like a traditional programming language. And that's what it eventually ended up being. So Kronos has a high-level functional declarative representation in source form, and it strives for efficient real-time performance. This is realized with the help of an LLVM-based compiler, which has both just-in-time compilation and static compilation available. LLVM has been mentioned before. Both Jan and Albert are using it in their projects, and I think it's probably the de facto standard to go to if you're developing a code generator-based compiler infrastructure nowadays. Right, so this is an example of how I wanted to design the language against both textual and visual programming. So the nice thing about functional data flow model is that the abstract syntax tree of your program is actually the same as the signal flow of your patch. So you can do a pretty direct one-to-one translation between the abstract syntax tree of the text to a visual tree or graph form, and it will make sense. Now you could, of course, translate, say, C++ into visual form just by translating the syntax tree into a graph representation. But that doesn't make quite as much sense because of the data flows that exist in C++ include implicit flows caused by side effects assignments. So if you were to do this kind of visualization for a C++ program, I think the visual form would actually be more difficult to follow than the textual form. Whereas in data flow, it's usually pretty natural, straightforward to think about programs in both ways. I model digital signal processing as discrete reactive systems. This term I got from Van Roy and his introduction to programming paradigms. And this basically just means that every signal processor will respond to a well-defined set of discrete input events with a well-defined set of discrete output events. So whenever there's an action, there's a reaction. So the data propagates from the inputs of the signal processor to the outputs. And this happens in synchronous manner. And that's the core of the signal model. So when designing this language, a key goal is hard real-time performance, which means that the code has to be more or less deterministic. So I don't want to jump into any routines that are uncertain in the sense of how long they will take to complete, such as memory allocation or other dynamic constructs. So I want the semantics of the language at runtime to be very simple, very low level, very static. And that will enable very efficient mapping to computing hardware of various kinds. Currently, I'm mostly focused on CPUs, but also on embedded chips. And incidentally, this model works well for GPU-like processors as well. And another important consideration is that the language is targeted for domain experts, which means music technologists, audio engineers, composers, people who work with computers and have interest in music and programming. So they are not computer scientists. And this has been a recurring theme in many talks in this conference, that we need to treat this case a little bit specially because the goals and the approaches must be different. And some features I adopted to consider this goal is that I wanted to give the language a simple syntax where the abstract tree of the syntax is aligned with the signal flow graph. So if you trace the syntax, you will trace the chord where the virtual signal travels, so to speak. I wanted the source code to mimic a dynamic language, mostly meaning that type annotations should not be present. And I also wanted a unified signal model so that you could program everything from, say, media streams to audio streams to user interface interactions with a similar signal model. And that's the sort of fundamental multi-rate signal model that the design of the compiler is based on. So to accomplish this, well, many of you may already be thinking that if you talk about looking like a dynamic language and hard real-time performance, then these two concepts don't really match that easily. So the solution here is a kind of two-layer approach to creating signal processors. And in fact, this two-layer approach is already present in many musical programming environments. For example, in SuperCollider, you have a functional language in which you create a graph of unit generators, which you then play. And I set out to formalize and extend this concept, meaning that when you program for Kronos, you program in the so-called meta language that describes a signal processor structure with a very high-level declarative approach. It's based on polymorphic function application and little else. So you can have functions that behave differently depending on the data type they receive. And this meta language doesn't see runtime values. That effectively means that if there's an audio signal traveling through the signal processor, the meta language cannot react or take into account the specific values at a specific time of any of those signals. So that's the technical constraint that makes this possible, that we can generate a static signal processor from a high-level representation and compile it into an efficient, performant machine code. And the intermediate representation that we generate from the meta language is the data flow language, which is really elementary, fast, and has a static signal graph. So the call graph of the data flow language is known, and that, amongst other things, makes this data flow language Turing incomplete. So you cannot write a word processor with this language. Well, I guess maybe you could, but you shouldn't. It would not be pleasant. It's designed solely for signal processing and focused on a particular range of problems in that domain. Right. So at this stage, I'm about to defend my work on the technology of this compiler stack. And I'm also looking forward to my next projects, which I want to fashion as dealing with the experience of learning to program, or the experience of programming. And that has connections to user interfaces and human-computer interaction. And know that I have this compiler stack I can play with, like a sort of experiment with different user interface paradigms and methods. And in fact, I'm 2 days into a new research project, so this is very early, but this is an excellent opportunity here at the conference to sort of discuss my initial ideas with you, perhaps receive some input and see where we could take this. Right. So if you talk about teaching programming, I think there's some essential reading that shouldn't ever be skipped. At the very least, you should read Mindstorms. Hopefully, many of you have. It's a must read for anybody who teaches programming. It talks about teaching children, but adults are just children that have grown over large. So it's the same thing. Then there's Chris Hancock, a Canadian, I think he's a professor nowadays, who has a great thesis about real-time programming and how it relates to computational literacy. So he wants to make computation more accessible by making it real-time, allowing people to have tangible results from their programs immediately. And that sort of rapid cycle of question response really helps learners to understand and internalize programming languages. And Brett Victor is a more recent YouTube trend kind of guy who is probably the person who's indirectly responsible for the creation of Swift, Apple's new programming language, which stole many of his ideas, or I shouldn't say stole, because ideas should be free. They should move from one place to another. But he has an online essay called Learnable Programming, which you should also check out if you haven't so far. So that would be my top 3 of essential reading and material to base the pedagogy of programming on. I think a recurring theme in all these ideas is that interaction is key to learning. The problem with some models of programming is that the sort of cycle of trying things and getting feedback is slow. It takes a long time, it's heavy. You write a big list of source code in an editor, you fire up your compiler, you wait for 10 minutes or 10 hours if you use templates, and then you get to see whether the program works or not. So what helps a lot in understanding programs and understanding how to write programs is if you're able to slice your programs up to manageable parts and focus on each one in isolation. You should be able to take a part of your program and see how it works, sort of on a drafting table or under a microscope. And that's hard to do with static compiled languages in the C tradition. Conversational programming is also a great asset in learning, as well as any creative programming, such as artistic, live coding. And in conversational programming, you need to have a rapid development cycle. So when you make changes in your code, you immediately see and hear what happens. I think it was Julian Rohrhuber who said that you need to hear what you're doing in order to be able to live code sensibly. So, further than that, the more ways you have at your disposal at observing the state and outputs of the program you have, in many ways, the more capable you are of gaining insights to how the program actually works. And I believe in visualization as a key factor in teaching, because multimodal communication is always more likely to reach a larger group of people than just giving them one stream of ideas. And discovery, the programming language and tools should make it easy to immediately find out how the things you're using were made. So if you're calling a function, it should be easy to find out what's in the function. Maybe even play around with it and make changes and see how it works. Okay, so none of these ideas are new in any way. They've been around for a long time, and it's easy to forget exactly how long. So let's take the birth of Lisp, for example. In 1959, Steve Russell actually managed to implement the eval function for Lisp, which is sort of the super function that makes Lisp possible. If you write that function, then you suddenly have an interpreter for the language. And McCarthy, who had designed Lisp, actually didn't believe that implementing this function was possible on the hardware at the time. But then Steve Russell, his employee, went and did it anyway. You should never listen to your boss. I guess that's the moral of this story. So in 1959, we get a Lisp interpreter, and 4 years later, Peter Deutsch wrote something that's called a REPL. Do you know what a REPL is? Has anybody heard about it? It's short for read, evaluate, print loop, which means that you have an interactive interface to your programming language where you type in some code, the interpreter reads it, evaluates it, prints out the result, and asks you for another input. And this is really a powerful concept. And most of the new programming languages that are coming up nowadays actually have a REPL. it's in fashion again. But for a long time, REPLs were kind of forgotten on the sidelines, mostly because they are very hard to do for languages like C or C++ or Java or anything that's statically compiled. And in 1963, Ian Sutherland actually went ahead and did a visual programming language. Let's have a little look if my internet works. Okay, let's not. You can find it on your own and have a look. Oh. Now it's probably coming from a
flowchart then would be sort of a diagram of the steps that you'd want the computer to take in solving some particular problem?
Yes, in fact, I have a flowchart on here. This is with Sketchpad again, and we have a demonstration of boxes representing statements to the computer to do some operation and compare some numbers and make a test and transfer it one way or the other.
This is the way the human being would like to set it up, by drawing boxes like this that represent different computations.
This is the way that a programmer normally operates, and then he has to transcribe this to some form like cards or something as an input. But here we go directly from him drawing the flowchart and stating what each piece is, putting the statements inside the boxes, to a compiled program which he may execute on the computer.
See. Well, you've shown us how you can enter numbers, say, by a typewriter, and now we can draw things for the computer directly. Are there other ways that you'd like to be able to communicate with the computer?
Well, we've been investigating here at the lab speech recognition and handwriting recognition for enabling the person to communicate better in those ways with the computer.
Okay, I'll stop you there. So that's 1963. So, functional programming was born ad nihilo, in effect, in 1959. 4 years later, we had an interactive programming environment, and elsewhere, a visual programming surface. So, the next 50 years would certainly bring wonderful advances, right? Or not. We ended up looking at something like this. Optimizing compilers and class-based objects for all their benefits became prominent and sort of removed everything else from the mainstream scene. So now in 2015, people are rediscovering many of these sort of semi-forgotten ideas and introducing them back into the mainstream of programming. New dynamic languages and functional languages and interactive programming environments are coming up all the time. So can we do real-time music DSP in a REPL yet? Well, we kind of can, but it's not as straightforward as you might wish. So that's something I set out to do. Let's try to make a REPL in which we can do elementary signal processing, where we can work on sample level, the level of primitive arithmetic instructions. And let's see if we can use that to enable people to learn fundamental signal processing in a more interactive way. So this is the REPL interface to Kronos. And this is a simple read, evaluate, print loop that's connected to a just-in-time compiler. So like in Pure, when you want to evaluate something, it's first compiled and then executed as native code. So my very first Kronos program would be here. Hello world, nice. And I can get crazy and start doing things like adding numbers. But what's more interesting is that you can actually also define functions. Let's say that the square is a transformation of x into x multiplied by x. So that's a function. So let's call it, and that's an expected result. And since it's functional, you can also use the concept of higher order functions. So let's try one of those. Let's call it map, which takes a function and a list. And it might look kind of like this. I hope I didn't make any mistakes. So now we have a simple function, and let's try using it with the other function we just made. So this is something I believe in teaching, that you don't come equipped with a huge framework of functions and libraries, that you actually show how to build things. And the language should be like simple enough that you can do that in practical terms. Right, so let's do another higher order function called fold, which you can use to combine elements in a list. So that looks kind of similar. Like so. Nap, not yet. So now I wrote two high-level functions, one of which applies a function to all sets elements in a list, and another that combines them using the function. Okay, so this is pretty standard stuff. Like every functional programming environment and language has these, more or less. But what makes it interesting is that we can deal with actual audio. So in this REPL, I can actually produce sound, which I do by defining a symbol called sound. Let me import the code first. Like so. So what just happened is that the compiler compiled a simple program to generate a sine wave and then patched it to your audio interface. Now, since the language is a bit special, you can also use this type of generator function as you would any other. So, for example, let's use the map function we just made. And then, oops, play a nice triad. So, the thing that makes it different from many existing languages is that you don't have a distinction between objects that generate sounds and functions. They're all functions, basically. And the reason this is possible is the fact that the data flow language that the compiler is built on has this static deterministic call graph. That way we can identify places where state is needed to generate a signal from a feedback relation, for example. I talked earlier about the ability.
So maybe I got lost, but what is this number when you send us the data, you get a number close to 1? What is that?
These. It'll just tell you the initial sample values, basically. It will evaluate this function and
to the initial sample.
Print it. So
somehow it's still operating over a string, right?
Sorry?
But somehow, even if it's returning, the value is returning you if I was using another function, how that will go to the initial sample to a set of samples? This is my question, because if the...
How to go from here to a streaming sound, is that the question? Well, basically, what's special about Kronos in comparison to many functional languages is that you can have stateful functions, so to speak. So if you were to call this thing again, you would get the next sample frames. Right.
Can you call it again?
Well, if I do it just here, it will just restart it, so it doesn't make a difference. But you can hear it, in fact, because it will play the consecutive output frames as a sound wave.
So can we say that here we just, because we compute streams and we need to print something, we just print the first value of each stream?
Yes. Actually, what?
I think those are the results of wave :scene applied to the three list members.
Yes.
Yeah. Okay.
So what precisely happens is that it actually builds different instances for the printing and sound purposes, but it's the same code anyway. So at least I think that's what it does.
I will just be a bit confused. I could just say it's a functional language. I will spell like the not to be stateful. So I will spell like the value of this map operation to return either one sample or a set of samples or a sample or an automata representing how to process samples. I will unspec it into different calls to be distinguishable.
Of course, and you cannot do that from your program. You can never see any side effects.
Any side effects, I see.
So the way it's done is actually the same way as in Forced, that you sort of lift signal memory to a language construct. So functions are pure functions of current and past inputs. In this way, you introduce a concept of time. But your user program cannot see this time. It can only see the current frame plus the delayed signals it has requested. So that way we can keep functional purity in the semantic fashion, but use state to generate efficient signal processes. And you may ask yourself, like, if you think about objects have usually identity, state, and behavior. So here we have state, but where does the identity come from? How are we able to associate a particular bit of state with a particular function call in order to keep the streams continuous and flowing? And that's trivially possible because the data flow call graph is fixed. So the state is identified by its location in the call graph.
And how did you schedule this data flow diagram? What is your approach to scheduling?
Do you mean scheduling of the machine instructions? Or?
Yeah, no, any data flow diagram has to need a schedule, which is in which order the nodes are fired. Because some nodes are depending on the input. Some nodes, the input of some nodes in a data flow diagram depends on the output of some other nodes. So actually, in general, there is not a unique schedule. For instance, a canonical example is the composition of two processes where a duplication happens. You can run the first process once and move the output twice, or you can actually run the process twice. So, depending, you know what I mean. So it's
yes.
typical. So what kind of a scheduling strategy are you using?
So what you're saying is the correct fact that in data flow language, you have a set of correct schedules.
Yeah.
And you can pick any of those correct
which one you pick,
schedules.
You have different implications. So which schedule did you pick for this?
Well, in this case, it's a heuristic algorithm that deals with, for example, register pressure in the CPU. So it schedules the instructions mostly because it deals with a very low level representation.
Well, I mean, but you will have to... okay, so you have like a candidate of nodes to fire next.
Yes.
And you select that, what you have. Then you have like an interpretation of how many registers this node is going to use or something like that.
Well, I will not go too deeply into this, but but what happens is that the node to be fired is selected based on what my compiler believes to result in the most efficient machine code.
In the most efficient way, okay, but yes. This will fix the schedule, okay.
Yes, it's fixed, yes. Okay, I think I should actually move on because the clock is ticking. So, REPLs are nice and wonderful, but it is, after all, 2015, and we have these remarkable things called video displays. the REPL is a product of the era where we used terminals where you could type a line and receive a line in return. And a long time has gone since then, and there are environments besides Emacs now, unfortunately. And what we need to think about when we develop further programming tools is how can we actually make use of this visual world that's in front of us. And we need to be careful because the basic concept of a REPL is so powerful that if we do too much to it, we can actually ruin the whole thing. So it doesn't need much, but we can do little things here and there and see if it actually helps us in our goals. So what I started to do here, and I've literally just spent 3 days on this piece of software, so please bear with me if it's not really complete, but we can build a web-based REPL, making use of the HTML as a presentation format. And this is the same thing you just saw. It's just piped through a web browser. And right. Sorry. Let's try that again. Right. So, as I'm hearing the present of my esteemed FOST colleagues, I'll do a little tribute to FOST by importing something called block diagram. And then I say that I'll actually want to use it. And what this does is to define a couple of custom infix functions I can use for block composition in the FOST model, so to speak. So, as a simple example, let's make a phaser. So we imagine this phaser to take as an input the frequency it should play at and output a signal. So I'll do a partially applied divide, so dividing the frequency by audio rate. At this point I want to upsample that signal to audio rate. And then I'll do this little fun thing called recursive composition. And this results in a function. Let's call it process. And see if we can actually get sound of it. So there's a visual representation of a waveform streaming out of this process. And I might want to make it audible. Doesn't sound so good, it's a naive phaser anyway. I'm kind of running out of time. Let's see. We could also use the types in Kronos to combine with this block diagram concept. Let's make a sinusoid oscillator in the same way. First, convert the frequency to cycles per second. Turn it into a complex coefficient. Resample to audio rate. And compose recursively with the identity function. Seems like I forgot a parenthesis somewhere. Should have been there. And now we actually heard a complex value signal, so it was out of phase. If I just take the real part, we can see a beautiful sinusoid coming out of there. But especially if you're teaching students signal processing, you need to teach them complex numbers at some point. I think somebody talked about the challenges of doing this. And what we might want to do is to show to them how the signals actually behave. So what I did in this visual REPL was a facility to actually stream kind of HTML from the compiler to the front end and just display it on the go. And I will not explain it in too much detail, but let's say that we just render this output like so. And from the same oscillator we get a pretty nice phasor representation. So one thing I haven't said anything about yet is the discoverability of things. So at this stage you might wonder, how does it actually do that? So we have a function called source with which we can look at what that render function looks like. And I won't bore you with the details, but it's essentially HTML encoded as sort of S expressions, which the REPL is able to translate back with the help of a library called Hiccup. All right, I think, what's the time?
10 minutes or 5 minutes until discussion.
Okay. So then maybe I'll show you one more thing. Let's design a resonator. This is a little function that generates coefficients based on the frequency and the bandwidth. So I'll give it just some numbers in cycles per second, and it gives me a set of coefficients to realize that filter. Let's make those numbers variables and assign this coefficient set to a variable. So now the definition of this symbol called reson for resonator is shown here. And using the same HTML facilities, I have developed a plotter for filters like this. Let's separate the FIR and IR part of resonator, so we get the feed forward coefficients and the feedback coefficients. Let's, no, not there yet, sorry. And then I have this function called resonator response, which produces a little function that can plot you the frequency response of that filter. Further, we can plot the magnitude. Oops. It's a demo effect. But anyway, that's a plot. My REPL crashed in there, so bear with me, please. I'll just replicate quickly what we had before. Okay, so there I have this nice image. But since the Kronos signal model is reactive, what I could do equally well is to give that parameter some life, like so. And this happens immediately when I assign a new definition to that frequency. as the graphics is actually a stream like the audio was before. So I think this demonstrates some of the initial things I've built for enabling the use of visual aids in a REPL to assist teaching for signal processing. And in the future, there's a lot of latent potential in that visual REPL. First of all, we should have control widgets. We should have sliders that you can assign those symbols. Any code you plot on screen from that source function that goes into the library should be live and editable. Why not? There's also the context and spatial aspect of programs. You should be able to organize your functions and your code in something other than a linear text dump. Like, there's no reason to do that anymore because we don't use teletype. We should build visualization libraries so that all of these plotting and visualization demonstration functions are easily used and accessible. And then moving beyond REPL, can we bring some of these features, these interactive conversational programming features, to patching interfaces, visual programming surfaces, multimodal programming surfaces with touch, other input devices? I sort of want to explore the space of interaction with a programming environment next, and this work I've shown here is sort of the first tentative step in that direction. So that's my presentation today. Thank you, everybody. If there are any questions or comments, I'll be happy to answer. In the meantime, if you want to play with the code, this is the main compiler repository, public, and this is the repository for the visual REPL. The compiler is written in C++, and the REPL is in Clojure, so you will need those if you want to build them. Thank you.
So, are there any questions?
So at the beginning of the talk, you discussed of PWGL, and so is there any plan, or it's already done, to integrate Kronos with PWGL, or?
We have done integration experiments with Mika, so we have some things up and running, but to formalize the interface between the languages and make it as dynamic and fluid as possible, that will take some thinking, and we haven't gotten around to that yet, so there's not a public release on that front yet.
So impressive work, congratulations, very nice. So I was wondering, what is your notion of rate in the system? So do you have a notion of rate, and if so, how is handled, for instance?
Rate,
Yes,
like update rate.
Like control rate, for instance.
Right.
You have like a different rate for control elements, a different rate for audio. Maybe if I upsample, I create a new rate, or is the same rate? What's the history of rate?
Yes. For example, in my REPL example where I did the oscillator, I upsampled to audio rate after generating the multiplier coefficient, and there was a function for that. So you can use functions to change the update rate at certain points in the program, and the update rate will then propagate from there on. So you can actually control the rate pretty arbitrarily in any part of your program.
Okay, so if I have a process with a very slow rate, let's say once a second, then my compose, which is also in parallel with a process that has a fast rate, like the whole latency goes like one to the slower rate then, or?
No, it will just dispatch to your slow routine once per second
I see.
within the audio loop.
Okay, that's simple.
Maybe one more question. Technical question, are you using the new MC JIT or the old one?
Well, what's the new JIT is the ORC. That's newer than MC, but I'm using MC.
MC, okay. Yeah.
LLVM question.
Yes. Okay, thank you very much.
Thank you.